Have you ever thought that black holes are a modern invention? Perhaps a brilliant product of 20th century science fiction? The name itself is actually quite recent. It was coined in 1969 by the American physicist John Wheeler, who needed a catchy term to describe a mysterious cosmic phenomenon. But the actual physics behind it, the idea of an object so massive that even light cannot escape, its grip is much, much older. It has been floating around the scientific community for over 200 years. Back in 1783, long before we had space telescopes or computers, a Cambridge professor named John Michell published a very strange paper. At that time, everyone accepted Isaac Newton's theory that light is made of tiny material particles called corpuscles. Michell reasoned quite simply, if light is made of particles, then it must feel the pull of gravity, just like a cannonball, a planet, or an apple. He asked a beautiful question. What happens if a star is so incredibly massive and yet so small that its escape velocity is greater than the speed of light? Michell realized that any light emitted from the surface of such a star would be dragged back by its own gravity before it could go anywhere. The star would be completely invisible to the outside world. He called them dark stars. It was a staggering insight. Yet this fascinating concept was completely forgotten during the 19th century. Why? Because scientists shifted their beliefs. They began to experiment with the wave theory of light, and back then, nobody could imagine how gravity could ever affect a wave. The idea of dark stars died out dismissed as a mathematical quirk. It wasn't until 1915, when Albert Einstein published his general theory of relativity, that humanity finally had the correct framework to understand gravity not as a simple pull on particles, but as the actual warping of space and time. Einstein showed that gravity bends the path of everything, including waves of light. The door to the black hole was unlocked once again. But ironically, even Einstein himself didn't believe that nature would ever allow such a monstrous, perfect trap to actually exist in the real universe. To understand how a black hole can actually be born, we first have to understand how a normal star dies. For millions or billions of years, a star survives because of a beautiful, delicate balance. Inside its core, immense nuclear reactions are constantly pushing outward. At the same time, the star's massive weight is constantly pulling inward, trying to crush it. It is an eternal cosmic tug of war. But what happens when the star eventually runs out of nuclear fuel? The outward pressure drops. The star begins to cool down, and gravity, having no opponent left, begins to pull the star inward, forcing it to collapse. In 1928, a 19-year-old student from India named Subramanian Chandrasekhar boarded a ship to England to study at Cambridge. He had no advanced laboratory, no computers, just a pen, some paper, and a brilliant mind. During that long, quiet voyage across the ocean, he sat on the deck and decided to calculate exactly what would happen to a star when its fuel was completely gone. Chandrasekhar discovered a shocking boundary in the laws of nature. He calculated that if a dying star is heavier than about 1.5 times the mass of our sun, the internal forces of its atoms can no longer resist the crushing weight of gravity. If a star crosses this specific threshold, now universally known as the Chandrasekhar limit, gravity wins a permanent victory. The star cannot stop shrinking. It is condemned to collapse forever into a single infinitely dense point. When the young Chandrasekhar finally arrived in England and proudly presented this groundbreaking discovery at the Royal Astronomical Society, he expected excitement. Instead, he met a wall of academic arrogance. Sir Arthur Eddington, the most famous and powerful astronomer of the era, and ironically Chandrasekhar's own mentor, stood up in front of the entire community and publicly ridiculed the young student. Eddington simply refused to accept the mathematics, declaring that nature would never allow a star to behave in such an absurd way. He called the idea of a star collapsing into nothingness monstrous. Because Eddington was so influential, the scientific community sided with him and Chandrasekhar's brilliant insight was dismissed and buried for decades. But history has a poetic way of correcting itself. In 1983, 55 years after that lonely voyage, Subrahmanyan Chandrasekhar was awarded the Nobel Prize in Physics for the exact calculation he did on the ship when he was just 19. The mathematics was real. Stars could indeed collapse forever. In 1939, right as the world was stepping into war, a young American physicist named Robert Oppenheimer finally solved the mathematical equations of this eternal collapse. He proved that it wasn't just a theoretical trick. Stars really could shrink to nothing. To help us visualize what happens next, Stephen Hawking came up with a famous mind-bending thought experiment. Imagine a brave astronaut standing on the surface of a massive collapsing star. Every second, according to his own wristwatch, he sends a flash of light back to his colleagues on a spaceship orbiting safely far away. Let's say he is scheduled to cross the boundary at exactly 11 p.m. As the star shrinks, its gravity becomes intensely strong, warping the very fabric of space and time. From the perspective of the spaceship outside, something deeply eerie happens. As the astronaut's watch gets closer to 11 p.m., his colleagues notice that the time between his light flashes is getting longer and longer. The signal sent at 10:59:58 and the one at 10:59:59 arrive just over a second apart. But the signal for 11 p.m., it will never arrive. Because gravity slows down time near the star, the light waves are stretched out to infinity. To the outside world, the astronaut appears to slow down to a complete stop, freezing right at the boundary. His image grows dimmer and redder, eventually fading into absolute darkness. He becomes a ghost, trapped in time at the edge of the universe. But what about the astronaut himself? His reality is much more continuous and much more brutal. As he crosses that critical boundary, the point of no return that we call the event horizon, he doesn't feel anything special at that exact line. Space looks normal to him. However, because a black hole is so extreme, the gravitational pull on his feet is vastly stronger than the pull on his head. As he falls toward the center, this difference in force stretches his body out, like a piece of spaghetti, tearing him apart, long before he even reaches the singularity, the point of infinite density at the very bottom. He has entered a place where the outside world can never see him, and from which he can never return. Once the astronaut crosses the horizon, the star continues its relentless collapse. But from the outside, something remarkable happens. As the star crushes down, it might be highly distorted, bumpy, or uneven. Yet, as it collapses, it releases ripples through the fabric of space called gravitational waves. These waves carry away the irregularities, effectively smoothing out the collapsing star. By the time the black hole settles into a mature state, it has sculpted itself into a mathematically perfect sphere. This led to a famous phrase in modern physics coined by John Wheeler: black holes have no hair. In science, hair is a metaphor for messy, complicated details. Wheeler meant that no matter how complex, deformed, or strange the original star was, and no matter what chemical elements it was made of, all of that information is completely erased from the universe during the collapse. A mature, non-rotating black hole, known as a Schwarzschild black hole, is the simplest object in the cosmos. It can be completely defined by just one single number its mass. But our universe is rarely stationary. Most stars rotate, and when a rotating star collapses, it forms a much more complex beast. In 1963, a New Zealand mathematician named Roy Kerr solved the equations for a spinning black hole. A Kerr black hole does not collapse into a single point. Instead, its rotation forces the singularity into a ring shape. Hawking noted that if you were to fall into a spinning black hole from the right angle, you might not hit the ring of infinite density at all. Instead, the mathematics suggests you could pass clean through the ring, falling through a wormhole into an entirely different universe. During this era of discovery, Hawking himself made a monumental mathematical breakthrough regarding the event horizon. he proved a rule known as the area theorem. The surface area of a black hole's event horizon can never decrease. When two black holes collide and merge into one, the area of the new black hole will always be larger than the sum of the original two. It was a beautiful law of cosmic geometry. Yet, despite all these brilliant mathematical equations in the 1970s, many scientists remained skeptical. How could anyone prove the existence of an object that by definition swallowed the very light needed to see it? To defend his life's work, Stephen Hawking made a famous bet in 1975 with his close friend and fellow physicist Kip Thorne. Astronomers had just discovered a massive invisible source of intense X-rays in the Cygnus constellation, orbiting a giant blue star. It was named Cygnus X1. Hawking actually bet Thorne that Cygnus X1 was not a black hole. He called it an insurance policy for his career. If black holes were a myth, his entire life's work was wrong, but at least he would win the bet and receive a 4-year subscription to a satirical magazine. By the 1990s, however, the observational data became overwhelming. The friction of matter being sucked into the invisible monster was creating the exact X-ray signatures Hawking's theory predicted. Hawking playfully conceded the bet, acknowledging that his equations were right, and bought Thorne a subscription to a magazine that, according to lore, made Kip's wife very unhappy. Despite all these brilliant mathematical equations on paper, during the 1970s, many scientists remained deeply skeptical. They argued that we shouldn't believe in things we cannot see. After all, how could anyone prove the existence of an object that by definition swallowed the very light needed to observe it? Stephen Hawking explained that while we cannot see a black hole directly, we can see its immense effect on its surroundings. Imagine a binary star system, two stars orbiting each other. If one of them collapses into a black hole, it will begin to violently rip matter away from its surviving companion star. As this stolen matter falls toward the black hole, it doesn't plunge straight in. Instead, it spirals inward like water, draining from a bathtub, creating a swirling disk of superheated gas. Due to extreme friction and gravity, this gas heats up to millions of degrees, blasting out a powerful beacon of X-rays into the cosmos. We cannot see the monster, but we can see the glowing crumbs of its meal. In the early 1970s, astronomers discovered exactly such a source. In the constellation of Cygnus, they detected an invisible object with immense mass blasting out intense X-rays while orbiting a giant blue star. It was named Cygnus X1. It was the first real candidate for a black hole. To protect his life's work, Hawking made a famous humorous bet in 1975 with his close friend and fellow physicist Kip Thorne. Hawking actually bet Thorne that Cygnus X1 was not a black hole. He called it an insurance policy for his career. Hawking reasoned that if black holes were just a mathematical myth, his entire life's research would be proved wrong, but at least he would win the bet and receive a 4-year subscription to a satirical magazine to comfort him. On the other hand, if he lost the bet, it meant black holes were real. His theories were correct, and his life's work was validated. By the 1990s, the observational data became absolutely undeniable. Cygnus X1 was indeed a black hole. Hawking playfully conceded the bet, acknowledging that his equations were right, and bought Kip Thorne a subscription to a magazine that, according to cosmic lore, made Kip's wife very unhappy. Black holes, once dismissed as an absurd mathematical anomaly, a mere ghost in Einstein's equations, are now known to be real cosmic powerhouses anchoring the centers of galaxies. But their true significance goes far beyond their physical size. They represent the ultimate boundary of human understanding. At the heart of a black hole lies the singularity, a place where the density of matter becomes infinite, and the warping of space and time becomes absolute. As Stephen Hawking pointed out, this creates a profound crisis in physics. Because the gravity is so extreme at the singularity, Albert Einstein's general theory of relativity actually predicts its own breakdown. It is a theory that calculates its own demise. At that single point, all our current laws of physics simply surrender. They lose any power to predict the future. Yet, to a true scientist, this breakdown is not a tragedy. It is a magnificent gift. When a theory breaks down, it means we have reached the edge of a new frontier. Black holes are the perfect extreme laboratories that nature gave us to solve the greatest puzzle in science: how to marry general relativity. The physics of the unimaginably large, with quantum mechanics, the physics of the subatomic world. By forcing us to look at a place where the infinitely large is crushed into the infinitely small black holes, are guiding us toward a deeper, more complete understanding of reality. They are not the end of physics, but the birthplace of a new kind of science. The event horizon is not a wall built to stop our curiosity. It is an invitation. It tells us that no matter how much we think we know, the universe will always hold a secret, waiting for us to be brave enough to stand at the edge and look into the unknown. And as Hawking famously teased at the very end of this chapter, it leaves us with one haunting question that challenges everything we thought we knew about these cosmic monsters. Are black holes really as black as they are painted?